Hello and welcome to Electronics with Emrys. In this video, we're going to run a few simulations in KICAD. I'm going to go ahead and put some timestamps up on the screen in case you want to skip ahead. If you follow along with me, we're going to start from creating a project all the way through to running a few different simulations. Let's go ahead and get started. I'm running KICAD version number 8. In order to create a new project, I'm just going to click on the new project icon at the top here. I'll give it a unique name. Whatever name you give it is going to become a folder, and all of your files will be inside of that folder. You can see that with my new project, I have a PCB file and a schematic file. We're only going to be working with the schematic file, so let's go ahead and get that open. Double click right here. And I'm going to maximize that. The mouse wheel lets you zoom in and out. And if you hold down the right mouse button, that allows you to drag the canvas around. The first thing we want to do is run a very simple simulation just to verify that our software is installed correctly. On the right-hand side, you can click on this icon, Add Symbol, or you can just press A as a shortcut. The first time you click on this, it takes a little bit of time to load everything up. I would usually cut this stuff out of a video, but in this case, I want to leave it because people are following along with me. It should finish up here pretty quick. There's a lot of different categories of components that we can select from here. I'm going to search for Spice. And you can see that that brings up a category called Simulation Spice. And there's quite a few different components in here that we can use. The first component I want is a DC voltage source. So I'm just going to go down to the bottom and select VDC, double click, and then click once to place that into the schematic. You can zoom in a little bit to get a little closer to this. And you can see that my cursor is still the place component cursor. When I left click one more time, it opens the symbol selection menu again. Now I want to grab the ground, which is just the 0 node here. Left click to place that, and then one more time left click to get a resistor out. Now the resistor doesn't show up in the Spice menu here, but we can very easily find it by just typing in RES, and the first component that comes up is the resistor. Left click to place that. Then I'm going to right click and hit cancel to get out of that mode. To change the voltage of my DC voltage source, I just double click on this one. I'm going to make mine 5 volts. And my resistor, double click on the R, and I can make that a 1 kilo ohm resistor. Now I just need to wire everything up. I'm going to select from this ground node. I'm just going to run the wire straight up. Click once at the corner, click again up here at this corner, then down at the bottom, and come across to close that, double click. The schematic editor will remove the wires that are going through components, so it just makes it a little faster to wire things up. Now we're ready to run our first simulation. At the top, go to Inspect and select Simulator. The simulator window will pop up. Then we're just going to click on Run. Because I haven't selected an analysis type yet, it's going to pop up and ask me what I would like to do here. And it's already selected on OP, the DC operating point test. So all I need to do is just click OK. And now I can see that my simulation was successful because at the bottom I have simulation results. We can see that our voltage source, V1, is supplying 5 milliamps. Our resistor has 5 milliamps flowing through it. The power supplied by our voltage source is 25 milliwatts, and the power dissipated in our resistor is 25 milliwatts. We also see that our voltage net is 5 volts, and that makes perfect sense. This is a really simple circuit, and we can see those numbers showing up in our schematic also. That makes it very easy to see what's going on. So now that we know that our simulator is working correctly, let's set up a circuit that's a little bit more realistic to something that we might build on a board. I'm just going to left click and drag to select the components on the left here, and then press the delete key on my keyboard to get rid of those. Same thing with these wires here. We're just going to select and delete those. And I'm going to move this resistor up, and by pressing R, rotate it to be at the top of my screen. One thing to note is that the simulation results are still showing here, so you can see that there are 5 milliamps flowing through this resistor, even though it's not connected to anything, and that's just an artifact of the already run simulation. Now I'm going to grab a couple more components. I'm going to press A to add a component. Then the component I'm looking for is a 2-pin connector. I found the easiest way to find this is to search for O1X02, and that brings me up a 1x2 pin connector. Double click and then left click to place one of these. Now I want to place another one of these because I want one for my input signal and one for my output signal on the board. So I'm going to select the one that I have here by left clicking on it, hit Control C to copy it, and then Control V to paste another one. And on the output side, I'd like it to be mirrored horizontally so that the connections are on the left side of the pins. So I'm going to press X once to mirror this. Then left click to place it. And then we're going to add one more component, which is going to be a capacitor. And another way to get out of this mode is just to press the escape key. Now I want to add a ground again, but I'm not going to use the simulation ground. I'm going to use a normal ground. There's no real difference except for the labeling on the schematic, but I want to show that these two are equivalent to the SPICE simulator. In order to add a ground symbol or a power symbol, we just press P, or we can click on this Add Power icon. Looking through the power port options, we're going to find quite a few things in here, but what I'm looking for is just a normal ground, GND. You can double click on that and then place it anywhere in the schematic, but I'm going to put it right below this capacitor. Press escape to get out of the mode. And now whenever I put my mouse over this node, it brings up the wire tool. You can also press W to start drawing a wire and escape to get out of that mode. I want to connect this pin 2 down to the bottom of my schematic to this ground. And then I want to connect ground up to this pin 2. So those are all the ground node. Then I'm going to connect the capacitor to ground, the resistor to the capacitor, the output to the RC node, and the resistor back to the input. Now I've already got a value on my resistor. I'm going to set my capacitor value to 1 microfarad, so 1U. Hit OK. And then my connectors don't currently have SPICE models. So in order to do an analysis on this circuit, I'm going to need to apply an input signal and have a measurement point. So on the left-hand side, I'm going to be putting in my AC waveform. I'm going to run a bunch of different frequencies through this, and on the right side, we're going to measure the magnitude and phase of those to see what happens to them at different frequencies. So we're going to make a Bode plot. To assign a voltage source to these pins, we're going to double click on the pins on the left, and then we're going to choose Simulation Model. Under Built-in SPICE Model, you can choose Voltage Source. And then we're going to change to AC magnitude of 1 and DC value of 0. Hit OK. Hit OK again. And now if we were to run the simulation now, we would see that there would be an error. I'm going to do that really quick for you. You don't have to follow along with this part. Mostly I just want to show that we're going to see an error down here. So you see error ngSpice DLL cannot recover and awaits to be detached. If we scroll up just a little bit, we can see that the error is in reference to J2. And that's because I didn't assign a model to the J2 connector. We can see that whenever I try to plot the voltages on the different nets, nothing shows up. So we're going to go ahead and close that out, and we're going to take care of this second connector. Double click on it, and now I have a couple different options to terminate this. I could add a small capacitance here. I could add a very large resistance here, or you can check this box that says exclude from simulation, and it'll just act like a complete open circuit, like there's nothing even connected there. Hit OK. And then I want to do one more thing, and that's to name my output node, so it's a little easier to identify in my simulation. So you can do this by pressing L or by clicking on the label option over here on the right. And I'm just going to name this out. Press escape to get out of that mode. And then I'm going to go to inspect and click on simulator again, run my simulation. And this time I'm going to do the same thing. I'm going to put 101 points per decade, 1 hertz to 1 gigahertz, and hit OK. And now you can see on the right, my top signal is called the voltage at /out. So I can see the gain and the phase here. I can plot both of those if I'd like. And I can also see the input, which is not really that interesting because that's measuring directly at the voltage source, so that's just a constant value. It is possible to zoom in on simulation results in here. You just use your left mouse button to draw a rectangle around the results that you want to see closer, and the results will pop up like this. In addition to being able to just zoom in and look at the waveform, you can also add cursors to any waveform. On the right hand side in the signal list, you can choose cursor 1 and cursor 2, and those you can move around. And then you'll see that the actual values are listed off on the right hand side here. You can also right click on a waveform and get different measurements. So for example, we can look at the maximum measurement here, and that measurement comes out here on the left side. I'm going to just discard this simulation again. And the next thing I want to do is add another component here. So what I'm going to do is I'm going to right click to drag this off to the left a little bit. And then I'm going to select this connector and left click and drag to move it over to the right. I'm going to remove these 2 wires here. And in between these, I'm going to be adding in a transistor. So I'm going to add a new component. It's going to be an NPN transistor. And in this case, I know I want an emitter base collector transistor because I'm after a 2N2222 transistor. Hit escape to get out of that mode. We'll connect up the emitter to the ground, and we'll connect up the base to this output here. And I think I'm going to rename this out to out 1. Zoom out a little bit. And for the sake of our fake board here, I'm going to put another 2-pin connector up here, and that is going to be where my DC source comes from. And here I'm going to remove the AC amplitude here and make this a DC source of 5 volts. Hit OK. OK again. And then we're going to connect ground to pin 2 of that. And pin 1 is going to be our VCC for this. I want to put a pull-up resistor in here, so I just copy and paste with Control-C, Control-V, and then R to rotate, and I'm going to place that in line with the wire. And I'll change that to a 100K value. And finally, I'm going to connect the output here to the output of the inverter I just made, and to the ground, of course. And then I want to name this output, and I'm going to name that out 2. The last thing I want to do is change my AC input to a step function. So I'm going to go into the simulation model here. I'm going to change device type from DC to pulse. And in pulse, I'm going to say that my initial value is 0. My pulsed value is going to be 1. Delay is 1 millisecond. Rise time 1 nano. Fall time 1 nano. Pulse width is, let's call it 10 milliseconds, and periods 20 milliseconds. And if you wonder how I picked those numbers out of the air, I have a 1K resistor, a 1 microfarad capacitor, so multiply those two together. It gives me my time constant of 1 millisecond. And I know that the rise time of a square wave onto this node is going to be about 5 times that, 5 milliseconds. So that gives me an idea of what time scale I should be operating at for this circuit. I'm going to move these options down here just so it's a little more readable to me. And now let's go ahead and try to run this without actually adding a model to our NPN transistor and see what happens. And before I go and try to run a simulation again, I'm going to add a SPICE directive directly into my schematic here. It just saves me a little bit of time whenever I go to run my simulation. So on the right side, you can click on the text icon, and a SPICE directive is going to start with a period. I'm going to put in tran because I want to run a transient simulation. I'm going to make the largest time step 10 microseconds, and I'm going to run this for 100 milliseconds. Hit OK. And then you can just left click to place this anywhere, and it'll be taken into your simulation whenever you run it. Hit escape. And now remember, we haven't actually put a simulation model in for Q1 yet, but let's see what happens when we try to run this simulation. Looks like we don't get anything out of it, and the simulator doesn't know what to do with that NPN transistor with no model. That's no big deal. Let's go get a model for it. I'm just going to search for SPICE 2N2222 because that's the type of transistor that I have. Looks like there's a model on the EEV blog forum. There's one on DigiKey, and I'm going to go grab this one from onsemi. If we left click on that, it automatically downloads. I didn't even have to visit the website. Then I can go into my downloads folder, and I've got the model here. I prefer my SPICE models to be of type MOD if it's actually a model. Let's take a look inside of this text file real quick to see what's in here. Here you can see that this is actually just a model file. It has comments at the start from the manufacturer, and then it has a .model statement that tells us all of the parameters for that NPN transistor, and there's nothing else in here. So this is a great candidate to be a .mod file. So I'm going to go ahead and close this out, and I'm going to change the extension on that to MOD. You don't have to do this, I just prefer to. So now that we have our model file downloaded, all I need to do is double click on the NPN transistor. I'm then going to go to Simulation Model, select File, and select the Browse icon from File. And I put this into my Downloads folder. You can see that a .mod file shows up here. Hit Open. And then be sure to select the actual model. Even if there's only one, this does not automatically select it for you. So you left click here and then select Q2N2222A if you're using the same file as me. That'll auto-populate all the parameters down here. You can take a look through them if you're interested in seeing what parameters were in that file. Hit OK. OK again. And now let's try running this simulation. You can see that our simulation was successful this time because we got a bunch of values that popped up. We can look at output 1, and that's going to be, as we expect, a slowed down square wave. When we look at our second output, that has an inverted waveform, and it's going all the way up to 5 volts, which makes perfect sense because we applied 5 volts from J3 to this 100K resistor, and that's what's pulling the output up when the transistor is off. And whenever the transistor is turned on, because there's 1 volt applied to the base, then it's going to be outputting a low state. It's pulled to ground. We can also look at how much current is being drawn into our transistor here pretty easily. Well, what if we want to see a calculation, something that's not one of these waveforms that's an option over here? Well, you can click on the user-defined signals icon here, and then we can add in our own waveform. So we could do something like the current of Q1 collector divided by the current of the Q1 base. And that would allow us to see the current gain of the transistor under the conditions that we set it up in. You can also take a look at the SPICE netlist if you're interested in seeing how the simulator put your circuit together. It's just a simple text file. This is going to be fed into ngSpice on the back end. So if you're curious about the syntax for this particular SPICE simulator, you can go check out the ngSpice manual. I'll put a link to that in the description. I'm going to go ahead and discard changes here again because we're going to do another different simulation here in just a second. Just to recap, so far we have very basic simulation capabilities. We can put in your regular RLC components along with a variety of other SPICE components that are built into this simulator. You can put in a transistor, a diode, or some other component that you have found somewhere on the internet and bring it into the simulator. And now I'd like to add in an integrated circuit. Holding Shift to select those wires and then dragging them over with the left mouse button. Let's go ahead and add an inverter. Let's say an HC04. It looks like we have a choice between the 74AHC04 and the 74HC04. They appear to be basically identical to me, and their pinouts are going to be the same. So I'm just going to grab the HC04, unit A, double click, and now whenever you place this, you're going to start placing all of the components here. So let's go ahead and put this one in series here with the output, and then the rest of them I'm going to put off to the right side. So we have channel B, C, D, E, and F. And then we also have the power connections for this. Hit escape to get out of that mode. Then I'm going to take this ground connection at the bottom, copy with Control C, Control V to paste it over here, and we will connect up the ground. Then I'm going to just connect up the VCC of that part to the 5-volt supply that we used for our transistor inverter. Before I forget, I'm going to label that output as out 3. Hit OK, and click to place that down. Hit escape again to get out of that. Now we want to connect all of these CMOS inputs to ground so that they have a known state when we're not using them. You'll see in a moment that it doesn't actually matter for our first simulation here, but this is a good practice to be in for the real world. Going back to the web, I'm going to search for 74HC04. And we can see that someone is asking for an ngSpice model for the 74HC04 inverter in the KICAD forum. We also see a TI product folder. And diodes, Nexperia, TI E to E. I generally like to use TI's models, so let's grab this one. On the HC04 website, we can go to Design and Development. Down here, we have Design Tools and Simulation and a Behavioral SPICE model. So I'm going to download that. Now this comes zipped up, so I'm just going to copy this out into my Downloads folder here. It looks like that the HC04 comes out as an HC05. So that's kind of weird that we get the HC05 here, because the 05 is an open drain version of the HC04. Let's see if that's actually the case, or if this is a misprint in the name. Just move that over a little bit because I might need to add a pull-up resistor if this really is an open drain simulation model. I'm going to double click on any of these components to get into the simulation model for U1. And U1 has one model for all of these. And you can access all the pins for that from this one component. I'm going to click on Simulation Model at the bottom, go to File, and we will select the HCO5.CIR, open that. Our model, now there's a few different options in here because there are different subcircuits in that library file. I want the first one, SN74HC05. I don't want to hit OK just yet. I want to go to the top here and look at pin assignments. So in pin assignments, I can see that pin 1 is not connected to anything. Let's click on that and see what options we have. It looks like our SPICE model only has 4 pins. We have an input, an output, VCC, and ground. So I can see in my schematic to the right here that the input is pin 1. So I'm just going to set pin 2 of our model to be pin 1 of our device. Pin 2 is going to be our output. And then ground is pin 7. You can see that over here. And VCC is pin 14. And you can see there's a little bit of a problem here already, is that my SPICE model only gives me 4 pins, whereas my actual device has a lot more pins. It's a 14-pin device because it's a hex inverter, not a single inverter. And this is really common for this type of simulation. A lot of the time you'll only get 1 gate for a multi-gate device. And I'm going to show you how to work around that. But first, let's try to run this simulation. We hit OK. And now we're going to go ahead and run our simulation again. And we can see that it looks like our simulation ran correctly. Let's look at output 1. There's our input to the base of our transistor. There's the output from the transistor, and then the output from the HC04 is totally dead. And what that tells me is that this really is an open drain part. So this is an incorrect model on the TI website right now. Hopefully by the time you get to this video, it will have been fixed, but I'm going to show you how you can get around this. Discard our changes. We're just going to add a pull-up resistor to the output of that device. I prefer to go with a 10K on the output of a device like this. So let's go ahead and run our simulation again. Looks like everything ran fine. We can see the output of our first stage, second stage, and the HC05 is outputting correctly. So that is exactly what the problem was. It's an open drain part. And you know what? For the sake of this video, I'm not going to go in and try to fix that or find a different model. It's not that big of a deal for what we're doing here today. Of course, you may want to modify the model, or you may want to make your own inverter model. I do have a video on the details of making your own SPICE models and what you can do to modify those models. So if you want to check that out, I'll put a card up here for you to link to that, so you can get into your own models and work on that. Because I mean, really, making your own inverter model is not very hard, and you don't need as detailed of a model as what TI is offering here. But if you want to run more than one channel when you only have a single channel SPICE model, then that can be a problem in this simulator. So let me show you how we get around that. All I'm going to do is duplicate the original file. And right click, drag it over here and hit copy here. I'm going to rename this to _hex. And you can name it whatever you'd like. This is just for my own information. I'm going to open a text editor. My favorite is Notepad++, but you can use literally any text editor to do this. We're going to go down past that top disclaimer, and we're going to create a new subcircuit. And personally, I think the easiest way to do this, just take an existing subcircuit, copy it, paste the new one in here. It doesn't matter if it's before or after the other one, but it does matter that you rename it. So I'm just going to add _hex onto this. And then I'm going to put all of the pins here for the 14-pin device. So I just happen to know the pinout of an 05 or an 04 device. So we're going to make that 1A, 1Y, 2A, 2Y, 3A, 3Y, ground. And on the opposite side, we're going to have 4Y, 4A, 5Y, 5A, 6Y, 6A, and VCC. Then I'm going to be calling subcircuits in here, and each of those subcircuits will be the original model. So we're going to have X1, and that's going to be connecting 1Y, 1A, VCC, and ground. And the order of these pins needs to be the same as the order down here, and then the name of the subcircuit goes at the end. The names of the pins need to match the names here. The names down here don't matter at all, except for telling you what order you need to be in. So then I'm just going to paste in 6 total channels, and I'm going to start renumbering all these. And sorry you have to live through me doing all this, because I want to do all this mostly in real time so that you can follow along and do it yourself. So now we have created a subcircuit that has 6 channels with 14 pins connected to VCC and ground, exactly the way we should for our model in KICAD. So I'm going to save this, close it out, and now I'm going to go back over here, double click on that component, sim model, and I'm going to change the file to the new file I just made. And with that new file, now I can select my model. So instead of choosing HC05, I choose HC05 hex. Hit OK. Oh, my mistake. Shouldn't have hit OK. Go back, simulation model, pin assignments, and then we're going to go in here and we're going to select the appropriate pin assignments. So now the pins should line up. We have pin 1 connected to pin 1, pin 2 connected to pin 2, and then that's going to be 3, this is 4, so now we've got AY, 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 and ground, and then YA, 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 and VCC. We hit OK again, and now we should be able to use all of these channels, and it won't give us any errors. So let's go ahead and wire this up. That's pressing W to add a wire on there. Connect that to the output of this, and then I'm going to use these guys to be wired together because this happens to be an open drain device. So I can connect the outputs directly together like this without any danger or problems. I'm going to add a capacitive load over here, which is going to be 50 picofarads, and a pull-up resistor of 10K. And we'll label this guy out 4. There we go. So now these in parallel will be driving this output node, and it'll be inverted from out 3. So let's go ahead and run our simulation. It's a bit beefier of a simulation than the previous one because it has more instantiations of those models. But it runs no problem, and we're able to take a look at our first stage output as it was before. Second stage is inverted from that. Third stage is inverted from there. And fourth stage is inverted one more time. So in this video, I've covered the vast majority of the basics you need to run simulations in KICAD. I'm sure there are an awful lot of different corners of simulation capabilities of KICAD that we can discuss in the future. So if you have any specific questions or issues that you run into, feel free to post them in my comments. I'm happy to make these kind of videos to help people out with getting started. So if you're left with any questions or issues, don't hesitate to ask. If you've made it all the way to the end of this, I want to say thank you very much for watching. and I hope you have a great day.